Hi everyone. In today's video, we're going to begin our discussion on alkynes. We're going to learn about the structure, acidity, preparation, and then reduction of alkynes to alkenes and alkanes. So the alkyne functional group is a triple bond functional group. And we should note by now that according to orbital theory, a triple bond is actually a sigma bond and two pi bonds. And this is what a triple bond would sort of look like according to orbital theory. So as you can see here, the yellow lobes are the sp and s lobes that are overlapping to form sigma bonds. And then the blue and red p orbitals are coming from the hybridization state of each carbon, and they are each overlapping to form pi orbitals. And as you can see, the electron density in an alkyne can really be described as encircling the triple bond, almost as if it's a cylindrical pi system that is filled with electron density. And so, if you're thinking about patterns in organic chemistry, one might see that the alkynes actually should have similar reactivity to alkenes, which is to say that alkynes can actually act as bases or nucleophiles given the electron density encircling that triple bond. But let's now consider the acidity of alkynes. Okay, so recall from your acid-base chapter that ethane has a pKa of 50, ethene or ethylene has a pKa of 44, and then your triple bonded CH ethyne or acetylene in this particular case has a pKa of 25. This actually means that ethyne or alkynes that have terminal CHs are actually relatively acidic, which is to say, an alkyne, in the presence of a strong base, such as your NH2 minus ion, can be deprotonated to form the conjugate base of your alkyne, which we call the alkanide ion, and then ammonia as your byproduct. So it's an acid-base reaction, so let's consider the pKa's of the acids on both sides. The pKa of your alkyne is 25. The pKa of your ammonia is 38. And so because the equilibrium of an acid-base reaction will favor the side with the weakest acid, therefore the equilibrium of this reaction will favor the formation of the alkanide ion. And so that means that your amide is a strong enough base to deprotonate your alkyne. And there are other bases that are strong enough to deprotonate an alkyne, and this is based off of the pKa's of their conjugate acids. So for example, H minus or your deprotonated ethylene molecule or your deprotonated alkane, these are the kinds of bases that you're going to need in order to deprotonate an alkyne. But not all bases are strong enough. For example, take your alkyne, in the presence of a hydroxide ion, you may consider an arrow-pushing proton transfer mechanism that can theoretically get you to your alkanide ion and water. But once again, the pKa of your alkyne is 25. This time, however, the pKa of your water is 15.7. And so the equilibrium of this acid-base reaction would actually favor the formation of your alkyne over your alkanide ion. In other words, the equilibrium will favor the left side of this reaction over the right side of this reaction. And so the reverse reaction here is favored, and we can actually use this particular reaction to our advantage. More to come on the next scene. Okay, so now let's consider how to prepare an alkyne in the lab. And the way we do this is through what we call a double E2 elimination of alkyl dihalides. Okay, so if you have a vicinal alkyl dihalide, it's vicinal because the two halide groups are adjacent to each other. Or if you have a geminal alkyl dihalide, that is a geminal position, that's a geminal relationship because the two halides are connected to the same carbon. Take any of these kinds of molecules and react that with a strong enough base, you are going to form an alkyne. So let's start talking about the formation of an internal alkyne. And we will use this geminal dihalide as an example. React that geminal dihalide with excess sodium amide and ammonia, you're going to get an internal alkyne. It's an internal alkyne because neither of those triple bond carbon atoms are connected to hydrogens. Okay, let's consider the mechanism of this reaction. So if you have this geminal dihalide in the presence of an amide, because the amide is a strong base, it's going to deprotonate one of the beta hydrogens in an E2 fashion to form this vinylic halide, okay? But because you are using a strong enough base, another mole of that base can deprotonate that beta hydrogen, once again in an E2 fashion, to form your alkyne. Okay, so now let's look at how you can form terminal alkynes. This time, consider this geminal dihalide. In order to form this terminal alkyne, this time is a two synthetic step reaction. The first step is indeed put in the geminal dialkyl in the presence of excess sodium amide and ammonia. But then you actually have to have a second step in water. And let's try to understand what that's about. But before we do that, just define a terminal alkyne. For an alkyne to be a terminal alkyne, the triple bond carbon atoms need to be connected to an H atom. So as long as one of the triple bond carbon atoms are connected to an H atom, it's a terminal alkyne. Okay, so now let's figure out the mechanism of this reaction. Okay, so in this case, there's only one beta position with respect to those geminal dihalides. And so your E2 reaction is going to look like this. To form this vinylic halide, and then just like last time, another amide ion can come in and go through another E2. To form your alkyne. However, remember that you are in the presence of excess sodium amide, and we already know that sodium amide is capable of deprotonating a terminal alkyne CH, which means that in the presence of sodium amide, which is excess in the solution, a proton transfer step is inevitable, and you would form this alkanide ion. And in fact, this is how we form alkanide ions in our synthetic organic chemistry. Take a dihalide that will form your terminal alkyne and treat it with excess sodium amide, and you form your alkanide ion. But if you really wanted the alkyne, you would then have to, second synthetic step, you would then have to react this alkanide ion with water. In this case, the alkanide ion is going to act as your base, which deprotonates your water. to form your alkyne back and then your hydroxide ion. And this process, the equilibrium favors the right-hand side because of pKa differences, as we've talked about in the previous scene. And so, if you're trying to form your terminal alkyne, you have to first treat it with the same excess sodium amide, but also wash it with water to protonate any of your alkanide ions that you will have undoubtedly formed in this reaction. And once again, this is actually that first synthetic step is actually exactly how we form an alkanide ion if we wanted to synthesize that particular molecule. And then lastly, in this video, we're going to talk about the reduction of alkynes. So just like alkenes, alkynes can also undergo catalytic hydrogenation. And recall that catalytic hydrogenation is the reaction of your pi bonds with hydrogen in the presence of a platinum catalyst. So just like your alkenes, if you react your alkynes with H2 in the presence of PT, which is your platinum catalyst, you also get your alkane as your reduced product. Although we didn't cover the mechanism for both of these reactions is actually very similar. So you can actually expect that it's going to go through two sequential hydrogenations. First to your cis-alkenes, and if you go to your cis-alkenes in this case, because your hydrogenation chemistry is a syn addition chemistry, and then another equivalent of your H2 in platinum will take you to your alkane. Note that using your well-functioning platinum catalyst, there is actually really no way to stop the reaction at the alkene. It will just keep on going to the alkane. So the question is, how do we now form alkenes from alkynes? There are two possible kind of alkenes that could be formed, however. We can form a cis-alkene or we could form a trans-alkene. Let's start with the formation of a cis-alkene. And the strategy here is to use a poisoned or what we call partially deactivated catalyst. So instead of using a fully functional catalyst, we can actually poison our catalyst so it doesn't completely go to the very end to form your alkane. And two common examples of poison catalyst are known as Lindlar's catalyst, which is actually a poisoned palladium catalyst, or using a nickel boron complex. This is also essentially thought about as a poisoned nickel catalyst, which is to say that if you reacted an internal alkyne with H2 under Lindlar's catalyst conditions or your nickel boron complex, you're going to get your cis-2 alkene preferentially. Now, to form your trans-alkene, we use a process called dissolving metal reduction. The reagent you use is a solid sodium metal dissolved in ammonia. Please note that this is not the same thing as sodium amide in ammonia. So these are actually two completely different reagents. So be very careful about that. We're looking at, in this case, solid sodium in ammonia liquid. So if you take this alkyne and react that with sodium solid dissolved in ammonia liquid, you're going to preferentially get the trans 2 alkene. And the mechanism for this reaction is going through a radical pathway, which we are not covering within the scope of our course. So ignore that in your chapter in your textbook. Okay, but the important thing to note is that once again, alkynes can be reduced all the way to an alkane by just simply reacting that using hydrogen gas on a platinum catalyst. If you wanted to form a cis-alkene, you would use hydrogen under Lindlar's catalyst or hydrogen under the nickel boron complex. If you wanted to reduce that alkyne to a trans-alkene, then you would react that alkyne in sodium dissolved in ammonia liquid. Okay, so that's pretty much it for the video. So we have learned about structure of alkynes, we've learned about the acidity of alkynes, how to make an alkanide ion. We've learned how to prepare alkynes using the double E2 elimination pathway, and then we've also learned about reduction of alkynes. Okay, thank you so much for watching, and I will see you in class.